Okay, we've been doing a practical here. We're looking at the bending of light as it goes into a prism. So if you look at your performance standards there, we're looking at designing the experiment here in a logical, coherent and detailed plan as an A standard. So the particular one you've been doing is you've actually been tracing a perspex block there. People have been sending an array light from an array box. They've normally dotted that point there on the line as it's come in, dotted it where it's entered, and put a dot there where it's actually left, and join them up with a ruler when they've removed their block, and then join them together and measured some angles to the normal. Okay, now it's okay to measure it from the surface to the incident ray and then subtract from 90 to get that angle there, and you can do the same thing here. You actually measure that angle sometimes with a G-aligner or a protractor and subtract it from 90 to get R there. So we're trying to compare I and R. So when you do your design, then you should come up with some sort of hypothesis about what you think the relationships are going to be between I and R's angles. Some people have said that I would be proportional to R, but any hypothesis will be okay. Your materials, then you list what the materials were that you used in this one. You talk about the safety that might have been a concern before you start the practical, just so you're aware to do this safely and maybe take some steps, and you'll put that into a sentence form. You can talk about your variables there. The independent variable is the one you selected to change yourself, and the dependent one would follow on from that. So that's obviously one of the angles here you're talking about for both of those. Controls are things you're trying to keep the same from one test to the other to make it a fair test. You describe them as well. And obviously the method you try and do step by step. What are you doing with the equipment, and what did you repeat? So you have to be careful there that it's actually clear and detailed and someone else could follow it. You need to give a labelled diagram there, so something like this will suffice, but some people are taking photographs these days and labelling that, and that'd be a good way of getting it. So as long as you're sort of meeting those standards, then designs that implements a logical, coherent and detailed plan, you'll be getting those sort of marks there as an A. This one's a clear plan and well considered, so there's a bit of difference in there. You keep an eye on how you manipulate apparatus there, and I keep an eye on that myself. Talking about the safety there obviously covers some of that though as well. Now you need to obtain, record and display your data accurately and highly effectively here. So when you come to do that, in this one here, you're talking about displaying of your results. So most of you can do a table and a graph to display these. So when you do your table, make sure your headings are clear, you're using the right units, and you're following on with the correct significant figures here. And ideally people would repeat an average there as they're sort of getting into the physics, rather than doing one angle there at a time and not repeating that. So a sort of thing might look like something like this here, I in degrees and R in degrees, and that's all your data collected. Now when you come to the graphs, you'd have to label that, give the right units, give a suitable scale, but obviously that's if you're hand drawing it. These days in Excel it will give you a scale yourself, but you still may want to adjust that. You should add a trend line through the Excel process and also display the equation, and that'll sort of display all your data together there effectively, hopefully. So when you look at this one here, you can do some calculations, and it turns out that I versus R does not give you a nice trend line that goes through the origin, so we're not getting proportionality there. So you might try other ones there, like I squared versus R, or I squared versus R cubed, and a whole range of other ones. But it turned out that when Snell did it himself, he eventually came up with trying sine of the angle in degrees versus sine of the R, and when you did that, he did get a straight line there, and this line almost goes through the origin there that I got from another group this week. You can see that it just misses there, so there's a slight error there, but that's okay. So that's the way we would display the table there. The graphs are there, and you'll get your good decent marks there. Other things to concern yourself with is you need to sort of make a connection between the data and the concepts when you're doing this there. You all should also evaluate your procedures and suggest a range of appropriate improvements and so on. We can look at the conclusion then of what we're doing. So when you're doing your conclusion, you can describe the trend of your data that you've got there. So in the first graph, you could discuss the fact that you don't get a straight line through the origin, so they're not proportional. But in the second one, you do, so you can talk about that as a trend there, that there seems to be a line of best fit that's straight and going through the origin or close enough to. So therefore, they're directly proportional, sine of I and sine of R. You should be able to form an equation from the graph. So you're thinking of y equals mx plus c in that case. When you're doing that, the y value in this case you'll find is the sine of R on the y-axis. The m with is a slope, you can read off your Excel there pretty easily. In this case, mine was 0.69, close enough, 0.69 there. You get 0.69 as your slope. And when you're doing your x value, it's sine of I. Sorry about the writing there. And you could actually have your add your c value on there as your y-intercept, but I'm going to ignore that here and say I've actually ignored it because it's pretty small. So that should be 0.69 there. All right, you've got an equation there. So you should then compare your results to your hypothesis. So if you did actually say there, if you fluked and said, I presume that the sine of the angle of incidence is going to be proportional to the sine of the angle of refraction, that would have been a pretty good hypothesis to go for, and so you would have been right. You may not have done that. In fact, most people won't have done that. So you need to now correct that hypothesis and say it turns out I was not proportional to R, but this particular one is. So compare it to your hypothesis. You should always do that. And then you try and use some physics concepts to explain what's going on. So you might want to look that up there and actually find out why is it bending there. It's to do with the change of speed there and change of the wavefront. And try and explain some of the stuff that's going on there to get some physics concepts in there. And that would make it a much better conclusion and analysis. You can also then compare to the real value there, and that will give you a comment on accuracy, but I'll come to that in a minute. Now, the last thing you normally do here is to talk about errors and improvements there, and you have to give that pretty detailed. So try and talk about random errors, explain why they're random errors, because normally they're due to be things that cause it to be slightly higher than the true value or slightly lower. It's inconsistent how big the error is and how much it is up and down. So be specific with this case, what would cause these errors to be random. And don't forget, you've got a fairly thick beam coming down there, and mostly you're using fairly small geoliners that might have, say, 1 millimetre is worth a degree, and these beams sometimes are 2 millimetres wide, so you're really having a trouble getting down with the resolutions that are smaller than 2 degrees there. Certainly smaller than 1 degree is very hard to do with what you've been using here. So that will give an random error as you look at it. You might view it at different angles and get a different parallax error there, and so on. Random errors can normally be minimised by repeating and averaging certain things, but be specific when you say what you're repeating and averaging. Don't you say, oh, I'm going to repeat and average. You need to say, what did you repeat and average, and what did you remeasure in that process? Try and discuss the scatter of the data points as well. If you were to see a graph that was actually something like this here, and that was your line you were going for, and you saw scatter points like that, the scatter of the data points that the line of this give you an idea of the size of the random errors. So that would be quite a few random errors going on there. If you had one that was actually like that, and most of the data points were fairly close to your line of best fit, you've got minimal scatter there. And you can link that to a discussion about precision then, because this is not very precise data because it's not being very consistent with what it's doing, whereas here you're getting more consistency. Sorry, that should be a straight line there. You can also talk about systematic errors, explain why they're systematic. It's that idea that you've got an error there that gives a consistent error that makes them all larger as the data value points or smaller than they should be. Sometimes it's a zero error in an ammeter, for example. You might be slightly above zero, so every current you measured was actually above it. So what could cause a systematic error here in your angles? So try and think. So you can then try and correct for that error. In the case of your ammeter, you would just re-zero the ammeter or replace the equipment and try it again. So think about what you could do with this equipment to try and actually sort of correct it. It may be that you'd actually be trying to plot a, you might actually go back up here. You've been trying to actually measure this angle here, in there, in I, and you've actually placed your geoliner there or something like that in this position here, but you haven't got this exactly lined up with the true face of the edge of the perspex there. You might have it slightly above because you've drawn a pencil line around that face of the perspex, so you're slightly above that, which means your angle is going to be slightly off. So there's things like that you can discuss as well. You can also then talk about the trend line there. If it does miss the origin, it's probably evidence that there is a slight systematic error if it was supposed to go through the origin. So some things and some quantities don't actually go through the origin because they're not proportional. They may be linearly dependent instead. But in this case, they should have gone through the origin, sine of I and sine of R. So it's probably a systematic error. So you can talk about the accuracy if you go and find the true value here. So if you go and look up Snell's law, you might actually be able to find out that there's a relationship there of sine I over sine R. And in doing that, for perspex, you might find that something like 1.45 as a guess. So if you can rearrange yours and get some sort of answer compared to that, and let's say you got 1.48 or something like that when you go and rearrange yours, if that's your value and that's the one that Snell's done there or the one that other people have done now, you've got an error there of 0.03 out of what it should have been of 1.45. And you can times that by 100 and get a percentage error there and talk about how accurate you were. So that gives you a chance to do it if you can compare it to the true value. If you want to talk about other improvements, then you can talk about ways you could have improved the safety then on reflection. You could talk about replacing equipment to reduce the systematic errors there. A greater range of data will make the thing more reliable, your experiment. So if you can try very small angles and also very large ones. You may decide to repeat the whole thing with smaller steps in your increments. So maybe go up 5 degrees and get a lot of data points onto the graph, and that'll improve the reliability. So there's the sort of things you can do in a basic practical.